From last lecture, we saw how to define the product measure on the product sigma algebra. So starting from this one, we're going to prove the main theorem of this entire lecture is basically the Fubini type theorem. So suppose I have a measurable function defined on the product space. I want to calculate the integral of this function on the product measure. And if you recall from maybe your multivariable calculus, this double integral, usually you can compute it by the iterative integral. So for example, you can fix a y first and then you integrate the x, and then you get a function of y, and now you integrate the y, and you can do the other way. Okay, so this type of theorem is called the Fubini theorem or Fubini-Tonelli theorem. We're going to look at under what condition can we say that the integral of f on the product space or the product measure is equal to this iterated integration. Okay, so that's our goal. So the proof is going to be quite technical, and I'm actually running a little bit different proof from Ken's course note. Okay, so I'll point out where the difference is as we move on. So in this first video, I'm going to set up a few lemma, and then in the next lecture, we're going to prove the Fubini theorem, all right? So first of all, just a bunch of definition and notation. If I have a two-measure space, x and y, then I can define the following notation. So first of all, if I have a set under the product space xy, so I define the E lower x to be all the y such that the xy is inside E. So here the x is fixed. I'm looking at what the y values are. Okay, so you can basically draw a picture. So if you have here x and y, and then you have some E, so you're basically fixing the x, and you look at what values of y that makes these x and y is inside E. Okay, so this is essentially the EX. Okay, so here is 1x. And you can do the same thing for y. And for functions, you can define something similar. Okay, so you can just, for example, take fxy, you fix an x, you treat it as a function of y. Okay, so you fix a x as a constant. Okay, you get it as function of y, and you do the same for y, you get f upper y. Okay, that's a function of x. Okay, so the first lemma or proposition we're going to prove is the following. So first of all, so if E is inside these product sigma algebra A cross B, okay, so if E is one of that, then what I can show is that these sections, these EX and EYs, they're both measurable. So measurable means in their respective set. So EX is a subset of Y, so this is really a measurable set inside the B, and EY is a subset of X, so this is inside A. Okay, so by measurable, I mean they're measurable in their corresponding measure space. All right, and second of all, I want to show that if you have F from X cross Y down to R, if that is a measurable function, well, then at least you can get the f of x and f upper y, they're both measurable. Okay, so they're measurable. Of course, the fx is a function from y to r, that's a measurable function from y to r, and fy is a measurable function from x to r. Okay, they're measurable on their respective measurable space. All right, so just one remark, as you may notice if you follow Ken's course note, what Ken did was that he started with two measures, and when he defined the product measure, he defined it as the completion of our product measure. Okay, so even if you start with two complete measure, their product measure in our definition may not be complete. So you really need a completion over there. Well, if you have a completion, then the measurable sets in this product space or in this completion of the A times B will be a little bit more difficult. Okay, so there if you follow his course note, you'll see he said, well, E is measurable if these two sections are measurable almost everywhere. Okay, and that's where the almost everywhere come from. I'm not going to do that, okay, because it's rather technical, okay. So for me, the product measure is just the measure may not be complete, okay. So we have these EX and EY and FX, FY, they're everywhere measurable. You don't have the almost everywhere. All right, so let's prove this fact. Okay, so let's prove the first one. All right, so I can do the following. So let's denote C to be all the F inside X cross Y, such that the Fx and Fy, they are both measurable. So basically, f of x is inside B and Fy is inside A. Okay. So this is a little trick of proving the first part. We just need to show that the C is in fact a sigma algebra, and if it contains all the boxes, then we know that it contains the A cross B. Okay, it contains the A cross B, the sigma algebra. All right. So first of all, why is that? So let's see. I have, if I give you a box, okay, A cross B, where A is in A. So if let E is equal to that, B is inside B, well then just follow from the definition, because you have a box, the EX, okay. If you think about what the EX is, well, is basically if your X is inside A, then you can always get B, okay. So it's either equals to B if the X is inside A, okay? Or if X is not in B, okay, then there's no way the X and any Y is inside the C, so EX is empty, okay? But in any case, you can see that this EX is going to be inside the sigma algebra. I should say A here, so so this EX, no matter what, is going to be inside B. It's either empty or the set B. And similarly for A as well, okay? So from there, we know that all of these boxes, A cross B, is inside this collection of sets C, okay? So now let's show that C is actually a sigma algebra, okay? So let's show C is a sigma algebra. Well, just basically checking all the definition of the sigma algebra. So clearly the empty set is inside C. That's fairly simple. And suppose you have a F inside C, okay, so say F is an element of C. Then if you consider the F complement and you fix an X, you look at F complement and you look at the section on X, well, you can convince yourself that's the following. That's essentially the F of X, okay, so that's everything not inside the F of X, so it's F of X complement, okay. And because f of x, by the definition of the C, is inside the sigma algebra B, so the complement is again inside sigma algebra B. Okay, and you could do the similar thing for the Fy, so you can show that the F complement is also inside C. Okay, so I'm not going to write the F complement on Y. Okay, that's basically the same. Okay, so you show C is closed under complement, and finally, let's take a countable union. So let's suppose let Fn, and going from 1 to infinity here, and greater than equal to 1, each of these Fn is inside C, okay? Well, so if you look at the union of these Fn and you fix an X, you look at what's the section over X, okay? That's, it's really easy to see that this is essentially the union of these Fx, okay? So here, everything is n greater than equal to 1. And again, each of these f of x is inside B, so their union is inside B. So this section over x is inside B, and similar for y. And I'm now going to write that as well. So you convince yourself this union is also inside the C. Okay, so we see that C is a sigma algebra. Okay, C is a sigma algebra. And because C is a sigma algebra and all the boxes A cross B is contained in C, and we know that the sigma algebra generated by these boxes is basically the product sigma algebra we defined. Okay, so we know that the sigma algebra A cross B is contained in C. Well, what does it mean by that containing C? That's essentially, by definition, as saying for every E inside A cross B, EX is inside B, and EY is inside A. Okay, that's by the definition of C. Okay, so there's a little trick. We show that when you do these sections of a measurable set, you get something measurable. All right, once we prove this, the next is fairly simple. So let's look at this. Okay, so if you have a f going from x, y to let's say real, if it's measurable. Okay, so let's consider y is f of x measurable. So f of x is given as a function defined on y to r. Okay, so the fy inverse of an element b, so let's take b inside the sigma algebra on y. Okay, then this is essentially all the, by definition, that's all the y. Okay, such that sorry, this should be x. All the y such that fx of y is inside b. Okay, that's just the definition of the pre-image. Okay, so this one, you can write the definition of fx is just all the x is fixed here, so f of xy is inside b. Okay. And if you look at this, well, if you think about what is f inverse of b, well, f inverse of b is essentially all the xy, where the f of xy is inside b. Okay. So we know because f is measurable, so this one is in the product sigma algebra A cross B. Okay. And if you compare these, it's getting clear that the fx inverse of b is essentially the f inverse of b, but you fix the x coordinate, you only look at the y coordinate. Okay. And because this one is inside A cross B, okay, because f is measurable, and I'm fixing a y and look at the section, and by part 1, I know this one is inside B. Okay, so this is by the part 1. Okay, so there we proved that the pre-image of fx inverse is inside B, so fx is measurable. And you do the same thing for fy. Okay, that's just follow similarly. All right, so now we proved these little lemma, and we need a little bit more preparation if we want to go to prove the tonality theorem. So there are really two ways of doing that, and I'm going to follow the textbook by Folland, and Ken is using the proof by Royden. Okay, so it's really quite different proof, but I prefer the one Folland. So we need to prepare a little bit. Okay, we need to give a little new definition. So this is something really technical, and as you may notice, I don't like too technical. So I'm going to skip a lot of detail. You don't need to know all these detail. Okay, so just for the sake of the proving the tonality theorem later on. Okay, so let's make some definitions. So let's define the following. So suppose I have a collection of sets. So let's say M is contained in P of X. Okay, I call it a monotone class. If the following happens, if, well, it's monotone, in other words, if you have an increasing chain of elements, say M1 containing M2 and so on, each of these Mi is inside this M, then you have their union, this countable union is also inside M. Okay, so it has close undertaking increasing chain. You also do the decreasing chain. So you have a decreasing chain of elements from this M. So each Mi again is from M. Then the intersection of these Mi is in M. Okay, so I going from 1 to infinity as well. Okay, so this is called a monotone class. And one thing you may notice is that the sigma algebra is automatically a monotone class. And you can also convince yourself you have two monotone class, then their intersection is a monotone class. So this allows us to define something called the monotone class generated by a collection. Okay, so let's let F to be some collection of sets, okay? Let's say inside P of X, okay? So we can define the generated monotone class to be the smallest one, okay? The smallest monotone class, let's abbreviate it for MC, okay? Smallest MC that contains F, okay? This is exactly the way you generate a sigma algebra. The sigma algebra is the smallest one. You contain the set, and you do the same for monotone class. And there's a nice little theorem called the monotone class theorem that basically says the following. So if your collection is an algebra, okay, so you start with some algebra, okay, so then you can generate two things. You can generate, on one hand, you generate a monotone class, okay, the smallest one containing this algebra. And the other one is a sigma algebra. You generate a sigma algebra, the smallest one, smallest sigma algebra containing this. Then, in fact, you have they're actually equal, okay? So this is called the monotone class theorem. This is a really technical proof. I'm going to briefly go over it. I'm going to skip a lot of detail, but here we go. Okay, so one direction is fairly easy because the sigma algebra, you know, is monotone class, and M of F is the smallest, so the M of F is clearly contained in the sigma algebra. Okay, that one is easy. Okay, so it's really just proving the other direction. Okay, so let's make the first notation. So let's say for every F inside this monotone class, in this algebra F, okay, let's define something. Let's define a new set. Let's call it C of F, okay. Well, C of F contains all the set E inside the monotone class of F, okay, so that, well, E take away, I shouldn't use curly F here, I'm looking at a specific F, okay, so I require E take away F, F take away E, and E intersect F. All of these three sets are inside the monotone class as well, okay, so inside that. Well, why do I care about this? Well, the idea is the monotone class, by definition, it only behave well under increasing or decreasing chain. It doesn't behave very well under union or set difference or complement, okay? So you want to make sure that if you want to show M of F is a sigma algebra, you want to see whether it's closed under, say, countable union, or at least under finite union and finite set difference. Okay, so that's the idea behind this C of F. Okay, so let's see what this C of F tells us. Well, so first of all, these curly F, because curly F is an algebra, then automatically you know that this curly F is contained inside the C of F. Okay, that's clearly is clearly true because all of these operations are closed for an algebra. And I'm now going to prove the next claim. You can verify the C of F, okay? This one is a monotone class, okay? Well, this is also, it's not too bad, okay? You can just follow the definition. You take a bunch of things in C of F. You only need to check it's closed under increasing chain and decreasing chain. And you can just follow the definition, okay? So this is something I'm not going to prove. So I'll say it's an exercise. Okay, it's really technical. Okay, but based on these two, what we know is that we have another monotone class, which is a subset of M of F, and it contains F. And because M of F is the smallest, and now I have a smaller one, so we know C of F is equals to M of F, okay? So basically, the goal is that now we can show the following. So for every E inside the M of F, and for every F coming from the original algebra, we actually have E intersect F and their set difference. So F take away E, E take away F, they're all inside this monotone class, M of F, okay? So that's the goal, all right? And now we actually want to show that the M of F is also closed under these three operations, not just for elements from F, okay? So now for every E inside the M of F, okay, you do something really similar. You define, let's say, C of E to be all the, let's give another, we have E and F already. Let's maybe call it G inside M of F, such that E take away G, G take away E, and G intersect E. They're all three of them always inside the M of F. Okay, so you do really similar stuff. And because you just show that for every E and every F inside F, you have this property. So clearly you have one thing, the curly F is contained in the C of E. Okay. And again, I'm not going to prove this one, but you can show that the C of E is also a monotone class. Okay, so this is the exercise. All right, but the point is, based on these two, what we know is, again, we have C of E, a monotone class containing F, so it's equals to the smallest monotone class. Okay, so we have there the same. Okay, so the end result, okay, after all these technical lemmas, basically what we showed is that for every E and let's say E1 and E2 inside the M of F, we have that E1 intersect E2, E1 take away E2, and E2 take away E1, they're also inside M of F, okay? And just because of this, you can now see that the M of F is going to be an algebra, okay? Because it's close undertaking complement, first of all, and close undertaking finite intersection. So using the complement of intersection is the union of the complement. You know that M of F is close under finite union, so it's an algebra. And moreover, because M of F is a monotone class, okay, and if you take En inside M of F, okay, then the union of these En is going to be a increasing chain. You can do the union of the union, okay, K, and going from 1 to K of the En, and use that K going from 1 to infinity, okay, so these are, because M of F is an algebra, you have each of these finite unions in M of F, and you're taking an increasing chain. The whole thing is inside M of F. Okay, so you have M of F is a sigma algebra. So M of F is a sigma algebra. And because it's a sigma algebra and it contains F clearly, so we have the other direction. The M of F contains the sigma algebra generated by F. Okay, so we finished this very technical lemma.